I can move from here. So I first start with some motivations. So the notion of infinitesimal symmetric category or Cartier category goes back to a paper of Cartier, in fact, of 1993. These categories are pre-additive, symmetric monoidal, equipped with an infinitesimal braiding that can be used to construct a braiding on the formal power series expansion of the starting category. We will see better this later. And what we want to do is first propose a more general approach to infinitesimal braidings that can be applied to arbitrary braided categories, so not symmetric, but just braided. So introducing the notion of pre-Cartier category, and then study a class of examples of pre-Cartier categories based on the category of left of modules and comodule over a quasi or a co-quasi triangular bialgebra. So first I start by following the definition of monoidal category introduced by Benabou in 1963. A monoidal category is just a vacuum of a category M with the distinguished object 1, the unit object, and a tensor product functor that associates to any pair of object, an object X tensor Y, and to any pair of morphism of G, a tensor product F tensor G. And we also have some natural isomorphism. So the first one is A, which is the associativity constraints that tells you that the tensor product of X tensor Y and Z is isomorphic to X and the tensor product with X and Y tensor Z. And the other two are the associativity constraint, so the left and right associativity constraints that tells you that X is isomorphic to the unit object tensor X and X tensor the unit object. And this associativity constraint satisfies the so-called pentagon axiom and triangle axiom. And you can see that the first one tells you if you start with an object of this form where all the parentheses are on the left side, and you want to arrive here where all the parentheses are on the right side, you can do two paths, let's say, and this must be the same. So you can first fix T and change the parentheses here, then do the associator with object X, Y tensor Z, and T, and you arrive here, and then fix X and change the parentheses here, and you arrive in this object here, or you just use associator with object X tensor Y, Z, and T, and then again associator. For the triangle one, if you start with an object of this form, what you can do is do right constraint here and fix Y. And this must be the same of do first the associator and then fix X and apply the left constraint on Y. When you have a monoidal category, you can define algebras and coalgebras in this category. I don't want to go into details in the general picture. We will see how this definition apply for the monoidal category of vector spaces. But if you want to define bialgebras and algebras, you need something more. You need a braided monoidal category. So this definition was introduced by Joyal and Street in 1986. A monoidal category is braided if you also have a natural iso between X tensor Y and Y tensor X for all objects X and Y in the category, such that these two diagrams commute. These are called hexagon. Now I'm just triangle because we are omitting the associativity constraint. And what these diagrams tell you is just that how can we flip an object A with a tensor product and vice versa. So if I want to flip A with B tensor C, what can I do? First, I flip A and B, and then A and C. And the second diagram tells you how can I flip A tensor B with C. First, I flip B with C, and then A with C. So in the obvious way, I would say. Moreover, if the braiding is involutive, the category is symmetric monoidal, and the braiding is called also symmetry. And the classical example of a braided of a symmetric monoidal category is the category of vector spaces, where the tensor product is just the classical tensor product of vector spaces. The unit object is the base field, and the braiding is the flip map tau. So tau is just the flip. Now, when we have this braided modular category, we can define bialgebras and off-algebras in it. And if we consider the category of vector spaces, in fact, we recover the classical notion of bialgebra and off-algebra that I want to recall here. So a bialgebra, H is just an algebra, so with product M and unit U, which is also a co-algebra. So we also have a co-product delta, which goes in the opposite direction with respect to the multiplication, and the co-unit from H into the base field, so opposite to the unit. This co-algebra must be also co-associative and co-unitar, so we have dual axiom of the associativity of the product and the unitarity of the product. But we also want that these two structures are compatible in the following sense. So the coproduct and the co-algebra are morphism of algebras, or equivalently, multiplication and unit are morphism of co-algebras. And you can see that are exactly this condition here. So these last two tells you that epsilon is multiplicative and unitary, while this tells you that delta, the coproduct, is unitary. While for this, with A1 and A2, we are using the Swidler notation. So this means just the delta apply on A. And you can see that this tells you that delta on a product of two elements is the product of the deltas, A1, A2, and B1, B2. We flip in the middle and we use the two multiplication. Of algebra is just a bialgebra equipped with a linear map S, which satisfies this compatibility condition. Again, here H1 and H2 are the coproduct applied on H. So we know that when we consider the category of modules, we can define a category of modules when we have an algebra. But if we want to give to this category a monoidal structure, we have to start with the bialgebra. In fact, if we start with the bialgebra and we consider the category of left modules over this bialgebra, we can associate to the tensor product of two modules. Here the tensor is just as vector spaces, a module structure. And this is the so-called diagonal action. So the action of an element H on an M tensor N is just H1 acting over M, tensor H2 acting over N. So, and again, H1, H2 is just the delta. So we compute the delta over H, then we flip, and then we use both the action, the one of M and the one of N. And the same unit object of vector spaces, so the base field, is also the unit object for modules. We just have to give to the base field an action, an H action, and we just use the co-unit. So you can see that, in fact, we need the delta and the coproduct and the co-unit to give the monoidal structure to the category of module. So one now can ask when this category is also braided. So when it is true that we have an ISO between X tensor Y and Y tensor X for any pair of modules. This is not always true and depends on H clearly. And in fact, it depends on if you are able to define a quasi-triangular structure on your bialgebra H. This notion was introduced by Drinfeld. So a bialgebra H is quasi-triangular if there is an invertible element R that we denote in this way with the Einstein summation, which is the so-called universal R matrix, such that these three axioms are satisfied. So the first one is a kind of commutativity between delta and R. It's also called quasi-commutativity. You can see that delta op, which is delta followed by the flip map, is not equal to delta, but you have R and R minus 1. And the other two axioms are the so-called hexagonal axioms. In fact, they correspond to satisfying the hexagonal axioms. And here we use the leg notation. So with R12, we just mean R tensor 1. If we write R13, here we mean that we put 1 at the second position. And the same for R23 is just 1 tensor R. If the inverse of R is the opposite of R, then HR is called triangular. And so, in fact, we have that the category of left modules over a bialgebra H is braided if and only if the bialgebra H is quasi-triangular. if this happens, in fact, the braiding are determined in this way. So for all modules x and y, you can see that here we apply the flip map on M tensor N, and then we act with the opposite of R. In fact, you can see that the second leg of R act on over N, and the first leg act over N. So we flip M tensor N, and then we act with RO.
Or you can also say you just act with R and then
flip. Yeah, maybe easier. Yeah, true. Thank you. And involutive braiding, so symmetric structure on modules corresponds to triangular structure. So that's due to Drinfeld. But now, if we look at, if we consider a bialgebra H, and we extend just trivially, so we consider the H linear extension of delta and M, we can consider the trivial topological bialgebra, formal power series in a formal parameter H bar. And now suppose to have a quasi-triangular structure on H tilde. So this is just an R, which is the something in H tensor H in degree 0 of H bar, plus something of degree bigger than 1 in H bar. And we can collect R from the left so that we have 1 tensor 1 at degree 0 plus something at degree 1, which we call chi, is just an element in H tensor H. And if R tilde is a quasi-triangular structure on H tilde, we can read this axiom at 0 degree, and we obtain just that R is a quasi-triangular structure on H. So the fact that this H tilde is a quasi-triangular structure at degree 0 tells you that also H is quasi-triangular with R. And so one can also read the axiom of this being quasi-triangular. That means exactly these three axioms here. So 1, 2, and 3 at first degree. And so you can see that now this chi is involved. And so one could ask, what are the properties of this chi? And these properties can be given, let's say, more in general when you start with a quasi-triangular bialgebra. In fact, you can see that the 0 degree order just tells you that your H is quasi-triangular. So when you have a quasi-triangular bialgebra, you can define a new, let's say, notion, which is this one, pre-Cartier bialgebra, if you also have an element chi satisfying these three properties. So these three are exactly the properties that corresponds to 1, 2, and 3 at degree 1 of H bar. You obtain exactly 4, 5, and 6. And you see that now chi commute with delta. And while for identity tensor delta over chi, you have now sum of two pieces. Again, we use the leg notation. And the second part involves R and R minus 1. And we call this chi infinitesimal matrix. So the first degree order tells you that a chi satisfies this property here. So it is in fact a pre-Cartier bialgebra. Moreover, we also say that this pre-Cartier is also Cartier if R and chi commute in this sense. And we will see later why this name, why pre-Cartier and Cartier. So first, an easy observation, if we start with an R which is in the center of H tensor H, you can see that here R minus 1 and R vanish to cancel each other. And so 5 and 6 tells you that chi is in primitive elements, tensor primitive elements. While 7, because of become equivalent to chi equals to chi of. Okay, and now, in the same spirit of the theorem of Drinfeld, we can state this. If we start with the quasi-triangular bialgebra, so we know that the category of left module is braided. This bialgebra is pre-Cartier if and only if we have a morphism, natural morphism in X and Y for all, in fact, X and Y module. You can see that this does not change the order of the tensor product. So X tensor Y goes into X tensor Y such that these two properties are satisfied. Also, here we have, in fact, the sum of two pieces, and the second part involves the braiding and the inverse of braiding, as exactly in this sum here. You see that here you have R minus 1 and R corresponds to your braiding. So, in fact, the T is T of the tensor T of X and Y tensor Z is the sum of these two pieces, and the same for 9. In this case, the T are uniquely determined from the infinitesimal R matrix. In this way, we just act with the infinitesimal R matrix. So you can see that we don't change the order. X tensor Y is sent into chi acting on it. So the first leg of chi acts on X, and the second leg acts on Y. And moreover, the pre-Cartier bialgebra is Cartier if and only if we have this commutativity between sigma and T. And so Cartier was this condition here, and you see that R chi was equal to chi of R, and now we obtain this condition here in terms of morphism. So sigma composed with T is T composed with sigma. So now we can give a categorical definition because we can call a pre-Cartier category just a pre-additive braided monoidal category and keep with the natural transformation T such that 8 and 9 are satisfied. So these two conditions are satisfied. If also 10 is satisfied, we call this category Cartier. And T is called the infinitesimal braiding associated to the braided category. So first of all, this tells you that if we start with the quasi-triangular bialgebra HR, the previous theorem tells us that this category is pre-Cartier if and only if the category of modules is pre-Cartier. And now, in fact, we can motivate the name pre-Cartier because if we now consider braided categories which are symmetric, so such that the braiding is involutive, and we also consider the condition 10, let's say, so the commutativity between sigma and T, we recover the notion of Cartier. So the notion of Cartier category. So just to sum up, Cartier category is just a pre-additive symmetric monoidal category with an additional T satisfying 8, 9, and 10. If you have 10, you also just need one of the two because you obtain the other using 10. So in our setting, we start with the category which is not necessarily symmetric, but just braided, and we just assume 8 and 9 instead of 10. So it is, and that's why we call it this category pre-Cartier.
Will you please clarify what is pre-additive category?
This is you see that you need to sum morphism, and with pre-additive, it just means that for any two pair of objects, the morphisms for RBM. And also the composition is distributed with respect to this operation. And so we can just sum morphism this way. And in fact, left modules are pre-additive, and yeah. And okay, so this is the notion of pre-Cartier, and when the category is symmetric and it is also Cartier, we recover the notion of Cartier category or infinitesimal symmetric category. Now, an example. So if we start with the field of characteristics different from 2, we can consider the Zwittler of algebra, so which is just the algebra generated by two elements, G and X. Modulo this relation, so G squared is 1, X squared is 0, and X and G anti-commute. The coalgebra structure is given. So G is group-like, so delta of G is G tensor X, and X is skew primitive, so delta of X is X tensor 1 plus G tensor X. And it is known that for the Zwittler, the quasi-triangular structures are classified and are of this form here. In fact, they are all triangular, so they are not just quasi, but also triangular, so the inverse of R is R op. And for this, we also classify the pre-Cartier structure. We have an exhaustive one-parameter family of infinitesimal R matrices given by this, so it is just XG tensor X with the scalar alpha. And moreover, if we also ask the Cartier assumption, so this one here, we just obtain 0. So Zwittler has no non-trivial Cartier structure, but it has pre-Cartier structure. So this is an example that, in fact, motivates our definition because there are no Cartier structure, but there are pre-Cartier structure for Zwittler. And now we also have some procedure to obtain new pre-Cartier bialgebra starting from pre-Cartier bialgebra. So for instance, if we start with the bialgebra morphism from H into H prime, the image through F of a pre-Cartier quasi-triangular bialgebra is still a pre-Cartier quasi-triangular bialgebra. Just consider the image through F of R and chi. So F tensor F over R and F tensor F over chi give you a pre-Cartier structure on the codomain. And so if you start with if you consider a bi-ideal, which is just so that the quotient is a bialgebra, it's just a two-sided ideal and also a two-sided co-ideal. So this means that the quotient is an algebra and a co-algebra, and it is bialgebra. If H is pre-Cartier, also the quotient is pre-Cartier. You can also induce pre-Cartier structure on tensor products. So if you start with the two quasi-triangular bialgebras, it is known that the tensor product is quasi-triangular, just tensorizing the two R matrices and flip in the middle. This is known, but you can also obtain, if one of the two is pre-Cartier, you can also obtain a pre-Cartier structure on tensor product. You just put one in the right place. And if both are pre-Cartier, so if you also have a chi prime, you can also consider the sum of these two, because pre-Cartier are from the vector spaces. This, of course, is not a classification on the tensor product, so it is just a way to obtain, let's say, pre-Cartier structure on tensor product when one of the two is pre-Cartier. Moreover, we can also use Drinfeld twist to obtain new pre-Cartier structure. So it is known that an invertible element in H tensor H is called a Drinfeld twist if these two conditions are satisfied. So the first one is the two co-cycle condition. The second one is the normalization property. And when you have a Drinfeld twist, you can deform the coproduct in this way here, obtaining a new bialgebra, HF. Say. And if the starting bialgebra is quasi-triangular with an R, you can also deform the R using the Drinfeld twist in this way here and obtain a new quasi-triangular structure. We prove a similar result. So if we start with something which is not just quasi, but it is also pre-Cartier, so we also have a chi, we can consider the new quasi-triangular bialgebra. This becomes pre-Cartier by deforming chi using, again, the Drinfeld twist and its inverse. So if we start with some pre-Cartier, we can induce pre-Cartier structure using morphism of bialgebras, using tensor products or Drinfeld twist, and so we are able to produce new example of pre-Cartier bialgebras. Now we can go probably to the main one of the main results about Hochschild cohomology. So if we start with the bialgebra, it is known that we can consider the so-called Kobar complex of H. So B0 is just the zero map, while B1 on an element X gives you one tensor X minus the coproduct on X plus X tensor 1, and so on. So B2 is just on an X tensor Y is one tensor the element minus delta on the first guy plus delta on the second guy minus the element tensor 1, and so on. So this gives you a complex, and the so-called Kobar complex. And the kernel of the Bn maps are the so-called Hochschild and cocycle, while the image of the n-1 is an coboundary. And we also can consider the cohomology group. And what we have is this. So if we start with the pre-Cartier quasi-triangular bialgebra, the following statements, which are equivalent, are satisfied. So our chi is always a Hochschild 2 cocycle, and this means what? It means that it is in the kernel of B2. If you put now chi here, you have one tensor chi minus delta tensor identity chi plus identity tensor delta chi minus chi tensor 1 equals to 0. That is exactly this condition here. So our chi is always a Hochschild 2 cocycle. And this is also equivalent to ask that the so-called infinitesimal quantum Baxter equation holds. And now we can say something more about this. And also these two guys are equal, but these two are exactly, I just come back into the definition, are exactly these two guys in the axiom. So these two are always the same. So you can see that the second part in 5 and the second part in 6 are always equal. So this is equivalent to ask that Chi is a two-core cycle and that the so-called quantum infinitesimal quantum Yang-Baxter equation holds. And what is the infinitesimal quantum Yang-Baxter? In fact, is exactly the quantum Yang-Baxter at degree 1 in H bar. So if you consider again the formal power series in the formal parameter H bar, and you look at the classical quantum Yang-Baxter at degree 1, is exactly this. Moreover, we have something more. So if we know that if we start with the pre-Cartier quasi-triangular, our chi is a two-core cycle. But if H is also Cartier, so our chi is chi of R, it is also triangular and it is an off. So we also have an antipode. This chi, assume that the characteristic is different from 2, is also a two-core cycle. So it is also a two-core boundary. It's not just a two-core cycle, but it is also a two-core boundary. In fact, it is just the image, 1/2 the image of this gamma here. Okay. Now, clearly, we also have the dual picture. So one can consider a quasi-triangular bialgebras, which corresponds to braiding of co-modules. And we can define pre-Cartier structure, which now are maps from H tensor H into chi, satisfying this axiom. These are exactly the dual of the axiom of before. We just you see that delta, before we have identity tensor delta chi, now we have chi composed identity tensor M. And this part here is exactly as before, but now we have to replace the product with the convolution product. I don't want to go into details what is a convolution product, but when you have morphism from a coalgebra into an algebra, naturally you have a product which is called convolution product. And now we have this kind of product instead of the standard product between elements. And we call this chi an infinitesimal R4. And again, this is Cartier. If R chi is chi of R, again with convolution product. So we just replace product with convolution product. And clearly all the previous statements holds, but now we need this dual version because in this setting we are able to produce other results, more precisely Tanaka-Crane reconstruction and also an FRT reconstruction theorem. So maybe I first give an example. So start with MQ2, which is just the algebra generated by 4 elements, alpha, beta, gamma, and delta, modulo the remaining relation. It is known that this is a bialgebra with comatrix commultiplication. So delta of alpha, for instance, is just alpha tensor alpha plus beta tensor gamma, so just as a product of matrices. And the co-unit is 1 over alpha and delta is 0 over gamma and beta. There is a quasi-triangular structure on this bialgebra, given by using the picture. And we are able now to produce a pre-Cartier structure for this, which is also Cartier. So we have an infinitesimal form chi, which is defined on homogeneous elements in this way. So chi on C tensor mu is just given by the epsilon on the product of these two elements, and we also have a scalar that is exactly the degree of the two elements. So when we start with MQ2, this is quasi-triangular, and this is also Cartier with this chi. Now we can consider the two quotients of MQ2, so imposing also considering also the quantum determinant condition, say. We can also consider these two quotients of GLQ2 and SLQ2. And it is known that the bialgebra structure and the R form descends to MQ2 and GLQ2. So these are quasi-triangular as well. But our Cartier structure descends only on GLQ2. So GLQ2 is also Cartier with the same chi, while this not happen with SLQ2. And moreover, we are also able to prove that for SLQ2, there are no non-trivial infinitesimal forms. Okay, maybe I can pass. First, I'll just skip this and see if there is time at the end. I first would like to speak about infinitesimal FRT construction. So, let's recall briefly the classical FRT construction. If we start with a braided vector space, So just a vector space V with a solution of the braid equation, see? An invertible solution of the braid equation. So suppose also that the dimension of V is n, we have a fixed basis, Vi, and also our braiding operator C is determined by these coefficients here. We know that we can define, we can consider a set of indeterminates, Tij, and consider the free algebra generated by this. This has a bialgebra structure given by this. So the delta of a Tji is just fixed I and j here, and then sum over k. And the epsilon over a Tji is just the Kronecker delta. Now we can define the two ideal in this free algebra generated by this relation here, and one can prove that in fact this is also two-sided coideal, and so this quotient is an honest bialgebra. So this AC is a bialgebra, and now there is the famous FRT theorem. So when we start with the braided vector space, we have a unique composite triangular structure on this quotient AC, such that if you consider the associated braiding, the braiding associated to the R, and we restrict to VV, this is exactly the braiding operator C. Precisely on generator, this R is defined in this way. If we consider TKI and TLJ, we just consider these are evaluated on this is just the coefficient C, KL, JI. You can see that here we flip the order of I and J. Now we want to do an infinitesimal FRT construction, so we will produce a new quotient. So we will quotient this AC with another B ideal, and we will induce some pre-Cartier structure on it. So we need, in fact, to give this definition of infinitesimal braided vector space. So an infinitesimal braided vector space is just a vector space, VC, so a braided vector space, VC, together with a T that satisfies these two conditions, and we will see where these are needed. Just an observation, any braided vector space is infinitesimal braided, considering just the identity with the scalar. So if we start with a braided vector space and we just choose the identity, this is infinitesimally braided. But now we are able to define a new quotient. So if we start with an infinitesimal braided vector space, so we also have a T defined by these coefficients T, K, L, I, J, that we obtain when we evaluate T on the elements of the basis. Then we define a new two-sided ideal in AC, which I remember is the quotient of the free algebra with the relations of before. And now we consider this IT as the two-sided ideal in it, generated by the same relations where we just replace the coefficients of C with the coefficients of T. So this is again a bi-ideal. And so this ACT is a bialgebra. So this quotient of AC with IT is a new bialgebra ACT. And now on this, if we start in fact with the infinitesimal vector space, we have a unique infinitesimal R form defined in generator in this way. So as before, but now we consider the coefficients of T and we don't flip the order of the indices. And just to clarify where the notions of before are needed. So if we start with the AC, we know that this is a quasi-triangular bialgebra. So we have an R. This R now descends to the new quotients if and only if the first equality and the last equality holds. So R passes to the new quotient if and only if the first and the last one hold. Moreover, our chi, which is defined on generator, so on the free algebra, descends to the first quotient if and only if the equality in the middle holds. So the first line, the first equalities are needed to obtain that the composite triangular structure descends to the new quotient and chi descends to AC. While this one is needed, is an if and only if, in fact, to obtain that chi descends also to the new quotient. So these are exactly conditions that we need. In fact, we have an if and only if. So the R of AC descends to this new quotient, and the chi defined in this way descends to the AC and to ACT if and only if the quality of V for all. So VCT is an infinitesimal embedded vector space. We also have a kind of vice versa. If we start with a pre-Cartier quasi-triangular bialgebra and we consider a left comodule, then we can define an infinitesimal embedded vector space in this way. So for C, you can see that we use the R, and we flip we change the order of V and V prime, while for T we use the chi and we don't change the order of V and V prime. So if we start with the pre-Cartier quasi-triangular bialgebra, we are able to define an infinitesimal embedded vector space using R and R. Moreover, as a special case of the previous theorem, the previous theorem says that if we start with an infinitesimal embedded vector space, there is a unique form on this quotient. But now we know that any braided vector space is an infinitesimal braided vector space with the identity, just with the scalar. So we can consider this case where we start with an arbitrary braided vector space. This is infinitesimal with the identity, and so we obtain a quasi-triangular structure on AC. In fact, in this case, ACT and AC are the same quotient given by this. So chi on the product of generators is given by what is just the epsilon on the products, and then you have some scalar and then that are exactly the degree of the homogeneous of the elements involved in chi. And these are if we want to you see that this example here, let's say this one here is exactly of this form. So MQ2 has exactly a chi of this form. Just the epsilon and a scalar that is exactly the degree of the elements involved. Okay, and now I would like to finish with some other example. So we know that we consider again the quasi-triangular setting. So again, elements of short maps. We know that Zwiedler is pre-Cartier. I just recall you how the chi was in that case. So Zwiedler has this quasi-triangular structure, which are all triangular, and the pre-Cartier structure have this form here, while just zero Cartier structure for Zwiedler. Now we can consider a family that generalizes the Zwiedler of algebras. So in fact, the En of algebras. So the En are generated as algebras by an element G and Nx. So now we have x1 into xn with this relation. So again, G square is 1 and xi square is 0 for all I. Again, G and the x anti-commute, but also xi, xj is minus xj, xi. And we have substantially the same coalgebra structure of the Zwiedler of algebra. And you can see that if we just consider the smallest case where n is equal to 1, we have just one x, and we exactly recover the Zwiedler of algebra. So just an element G and an element and an x. It is known that also these off-algebras are quasi-triangular with some quasi-triangular structure that I didn't want to recall, but this depends on some matrices, some n times n matrices. And if these matrices are triangular, the structure are triangular. Also, they are not just quasi, but also triangular.
And it's not only some, it's all, right? You can take any combined matrix, you will get an R.
Yeah, for any matrix, exactly. For any n times n matrix, we have a quasi-triangular structure, and these quasi are triangular if and only if your starting matrix is symmetric. And in fact, for the Zwiedler case, which is just E1, this is just one element which is automatically symmetric, and in fact, all the triangle or the quasi-triangular structure are triangular in the Zwiedler case. And now here to prove to classify the infinitesimal matrices is not so easy. In fact, we first classify the two cocycles. In fact, we know that an infinitesimal a chi is always a 2 cocycle. We have seen before in our result. And what we can prove is that, in fact, the second cohomology group has this dimension, so n times n plus 1 over 2, with this basis. So this means that an arbitrary 2 cocycle for En is just a 2 coboundary plus this other part here, where we just have Gxi tensor XL for all I and L, let's say. And now on this, we impose the pre-Cartier axioms. So these simplify a lot the computation. So we first classify the 2 cocycles, and then on this, we impose the pre-Cartier axioms. And we obtain, in fact, that for the En, for the quasi-triangular of algebra En, we have an exhaustive infinitesimal family of infinitesimal R matrices given by this. So you can see that this is a sum of these tensorons here, where we have G, XP tensor XQ, and P and Q goes from 1 to the N. So these pre-Cartier structures are associated to a matrix of these coefficients gamma. And these are Cartier if and only if this matrix is antisymmetric. So in fact, here we can also recover this Widler case. And moreover, we can also say something more. If we start with an infinitesimal R matrix, this is not just a pre-Cartier, but also Cartier, if and only if it is a 2 coboundary. So this is, and then this allows us to do some, say, quantization. In fact, we can prove this more general result that when we have a pre-Cartier quasi-triangular bialgebra and some chi, which is an nilpotent element, if these 2 conditions are satisfied, and these are exactly, so this is the first guy, maybe I can just show you, in the axiom of pre-Cartier, in the axiom of pre-Cartier, are exactly this must commute with the second one, and this must commute with this one. So if these are satisfied, we can obtain, just using the exponential, a quasi-triangular structure on the formal power series. So if these 2 conditions are satisfied, we have a quasi-triangular structure on the formal powers, on the trivial topological bialgebra, given just by R, which multiply the exponential of chi. So, and so we can apply this to the En. We know that En has this pre-Cartier structure, and so we obtain this new quasi-triangular structure on the trivial topological bialgebra on En, given by this. So it's just the quasi-triangular structure of En, which multiplies this sum till chi to the N. In fact, chi to the N plus 1 is 0. So the sum is finite, and this is the quasi-triangular structure. So when we have, in fact, this pre-Cartier satisfying these 2 conditions, we are able to obtain a new quasi-triangular structure on the formal power series expansion of the bialgebra. But these structures are also rare. In fact, we have some no-go theorems. Let's say we have some big families also of algebras. We have not this chi. So I don't want to go into detail, but if we consider the generalized, for instance, kappa-Newton of algebras, where that as the smallest example as the classic, the well-known kappa-Newton of algebras. I don't want to go into details. This has just trivial infinitesimal R matrices for all the quasi-triangular structure. If the kappa-Newton is the only case where this has 2 quasi-triangular structures. So, and yeah, the problematic part was for this other part, for this quasi-triangular structure here, because for this one, this does not contain Z, which, as you can see by this relation, is the problematic part, let's say. This is easy to prove that the only chi is 0, while for this is a bit more difficult, but we can use the fact that these kappa-Newton are semi-simple, and so 2 cocycle coincide with 2 coboundaries. And so this helps to prove that, in fact, just the 0 chi. And also, if you generalize this Widler in the direction of Radford of algebras, which again generalizes Widler in this setting, if you have G and X, but now different, let's say G to the N is 1 and X to the N is 0, and XG now is Q to G, QGX, where Q is a primitive roof of unity. Now, if you consider the smallest case, you recover this with the of algebra, and we know that this is pre-Cartier. If now R is 1 and N is bigger than 2, we have Taft algebras, but we know that Taft algebras have no quasi-triangular structure, and so no pre-Cartier. So it just remains to study in the case when R is bigger or equal than 1, bigger or equal than 2. And also in this case, it is easy to prove that there are no non-trivial infinitesimal matrices. So we have families where we have just chi0, but also example like MQ2, GMQ2, or in fact the EN, where this chi exists. And if this chi exists, they are a powerful tool because they allow you to obtain some quasi-triangular structure on the formal power series expansion of the bialgebra. So they are rare but powerful, I would say. So I think that it's all, and I thank you for your attention.
Thank you very much. Some space for questions, remarks.
So from the braided chronology category, you get an action of the braid group.
Sorry, I don't hear.
From the braided chronology category, you have an action of the braid group. Is there some analog of this for infinitesimal braided?
I don't know. I don't know. I don't know.
There is something called a Cartier ring, and you get a representation of this ring. Okay.
Ah, okay.
In this way, you are able to categorify or classify all pre-Cartier structures by some social cohomology technology. And
you just know that your pre-Cartier are 2 cocycle. So in some cases, it's useful to classify these 2 cocycle, and we did for EN. But yeah, in general, it's not so easy then to classify them. Strategies usually you maybe classify 2 cocycle because there are some tools to classify them. For instance, for the EN, you look at them as a bosonization. So the EN is a bosonization of the group light part and the nilpotent part. And so you can use some cohomological results that tells you that the 2 cocycle, the second cohomology group is just the invariant part of the cohomology group of the part with X. So you can use some tools for classify 2 cocycles, and maybe then you impose that. But in general, we just know that they are 2 cocycles, and in some cases there are also 2 coboundaries. So.
This result one to matrices. That's not correctly, especially when you consider like 2 by 2 matrices. But if you consider, let's say, a higher dimension of 1, something more.
Yeah, we don't know about SLQ1, for instance. We know just that for SLQ2 there are no proposals, but for SLQ1 we don't know. Yeah, that's to be done because computation, but would be interesting. Yeah.
Could it somehow be used to construct kind of integral systems?
Yeah.
Somehow kind of interpolate R matrices and classical R matrices.
Yeah.
This is true, and something that you didn't mention. So also a special case is in fact a classical R matrix.
Yes.
Yeah.
And this was also kind of what motivated us to think of this way quantized. Because for them, you know that you can build starting from a classical R matrix and build the quantum one. And we just wanted to prove a similar theorem in this whole algebra setting. And of course, it's much more complicated because you don't have a semi-simple Lie algebra, so you don't have white lemmas and so on. But still, we thought yeah, mainly this quantization direction. Kind of using this structure, you can find another R matrix on
Yeah.
Yes, composition the structure, because many observed many years ago, even from this you can construct like a very different It's the extra information that you have, if you have anything.
Yeah, we try to do something in this direction, but yeah, we define a calculus with using the chi, but we don't know yet if this is a portion of this bicovariant calculus. And we want to understand this better. Yeah.
So if you go to the axiom of the client, because this really looks like a bidirectional field. It's like if you insert something, there's always a lens rule. And so in fact, you can show you fix one element, this gives you a vector field calculus that then really is a different calculus. This works well.
Yeah.
But,
In the sense of probably it's
Yeah. Yeah.
Okay, any other question? Not the case, let me speak again.
or very different levels. Yeah, not really listed.
Yeah, like